Hi everyone and welcome to the demo of iHealthEmergency. The project consists in an IoT platform that provides monitoring tools to be always present for your patient. He wants to help you in your job as a doctor, as a caregiver, and above all, he wants to increase your confidence as a patient. iHealthEmergency can track the physical activity of a single subject and constantly get information from the environment. Indeed, you can in any time ask for help just talking to the system. It will provide for you an immediate assistance thanks to its emergency service always up and running. This is the use case of the system. As we can see, it provides two types of communication protocols. A RESTful protocol used to synchronize each device and each service to the system, and an MQTT protocol used to exchange data between components in an asynchronous way. The catalog is the main actor that orchestrates the registration of each component to the system. This is why each device has a JSON sectim file that contains the catalog IP address. Let's make an example. Supposing that a device from Raspberry wants to access to the system, it will get from each JSON file the catalog address. Through a PUT request, it connects to the catalog and asks for system information. On the other hand, the catalog has its own JSON sectim file in which are contained all the network information. In this case, the catalog will return to the Raspberry the information needed to establish a communication with the message broker. This process makes the system more scalable. For example, if in the future we want to update the system or enrich it, adding a new device that handles the same communication protocol. Once the registration is made, the catalog maintains the status of each device is always updated. To do so, it waits for the device activity for a bunch of seconds, and if, for any reason, the device does not expose any activity, the registration is cancelled. Let's see how this works. As we said, the registration is made for any devices, but here we show an example using the wait patient. Once the device is launched, it's registered to the catalog, but until we do not type the simulation that we want to perform, we are not actually sending data. This is seen by the catalog as inactivity, and this is also why after 10 seconds the wave is removed from the list. We now type our choice from the menu of the right side. Now the wave is re-added by the catalog, but this time we make a PUT request each 5 seconds in order not to be removed again. All the devices placed on Raspberry Pi, as we said, have to be registered to the catalog using a RESTful communication protocol. With the same protocol, they also send data to other two components, Telegram and Freebird. On the other hand, they communicate with an MQTT protocol with the message broker, in order to provide constantly data to the control strategies. To make this process easier to understand, we show how each device works by visualizing their own data directly on Freebird. But which devices are we referring to? We've already talked about the wait patient. It's a wristwatch activity tracker that works just when the patient is wearing it. It returns number of steps, heart rate, body temperature, and it also works as an accelerometer, useful to predict if the patient has probably fallen. Once Freebird is launched, it's registered to the catalog as we already seen for the wait patient. We are now simulating through the wave tracker a normal situation in which the patient is just wearing the watch. We can see on Freebird how its parameters are updated in real time. The second device on Raspberry is a motion sensor. This device is not strictly related to the patient because it's monitoring the entire environment in order to activate the system if any movement is detected. As always, the motion is launched and registered by the catalog. As we can see on Freebird, no movements are detected until an end movement changes the motion status. The next device is a microphone. It's used to record a voice message asking for help. As the motion sensor, it retrieves information not directly from the patient, but it's listening to the environment. In this way, anybody can ask for help. The microphone is launched, and its status is always updated on Freebird. As we can read here, it's always listening and waiting for an help request. The last two devices are LEDs, a green LED and a red one, and they are used to handle the control strategies. They are codes that analyze data coming from the system, and based on some constraints, they manage the behavior of the system. The first control strategy is the user presence control. It provides RESTful communication to register and retrieve information from the catalog, and an MQTT communication to retrieve data from the devices placed on Raspberry Pi. The aim of this control block is to handle the system status in turning on or in sleep mode. The two devices involved are the wake patient and the sensor motion. This means that if a movement is detected or the wake patient is worn, the system is turned on. First, the Raspberry acts as a publisher to publish data to a certain topic. The user presence control analyzes this data and sends back the result. To do so, it is now a publisher while the Raspberry is a subscriber. If one or both of these two devices is detected, the visible effect is provided by the green LED, indicating that the status of the system is switched on. If both of them are not detected, the system status is switched to sleep mode and the green LED turned off. Let's see how this works if the two devices are run separately. From the wake patient device, we first simulate that the patient is normally wearing the wristwatch, typing 1 from the menu. In this case, we are publishing the patient data and the user presence control is subscribing to retrieve them. As a result, it returns the control to switch on the system status. It means that the green LED is turned on and the status on Freeboard is updated. Now we run the motion sensor and we select from the wake patient menu the second choice that simulates the inactivity of the watch tracker. This is read by the user presence control as a total absence of activity and returns the system status in sleep mode. This happens because even the sensor motion is not detecting movements. But once it detects something, the system is turned on again. The second control block is the emergency control. It provides RESTful and MQTT communication. The aim of this control strategy is to handle the patient status and to analyze data in order to define if the patient needs assistance. The two devices involved are the wake patient and the microphone. Indeed, the emergency call starts if some patient parameters are abnormal or if the microphone detects a voice help request. As before, the Raspberry acts as a publisher and the emergency control as a subscriber. It then analyzes this data and sends back the result. To do so, it is now a publisher while the Raspberry is a subscriber. The final result is that the patient status is switched to not safe mode and the red LED is turned on. Immediately, the system sends a message to Telegram advising the person in charge that an emergency occurred. Let's see what happens if the patient falls, typing the third choice of the simulation menu. As before, the main actors are the emergency control and the Raspberry subscriber. The wake patient is now publishing data that after 10 seconds will simulate a strong variation of the accelerometer in the Z direction. The Raspberry subscriber will retrieve the controls to change the emergency status. As we can see, the red line is turned on and the patient status on Freeboard is updated too. Let's see now what happens if the heart rate of the patient increases constantly, typing the fourth choice of the menu. Again, we have the same actors. After 10 seconds of high heart rate values, the system considers it as an emergency. The last device to present is the microphone, and it has a crucial role in the emergency system. This device is always on and ready to call the emergency status if needed. If the help message is detected, as before, each components change their status.
Aiuto!
With this video, it's also evident how immediate is the reception of the Telegram message. It is received in all emergency cases, therefore also for the previous simulation. Telegram helps you to be warned in case of emergency wherever you are, providing you also to access immediately to the Freeboard platform and check what happens in real time. We hope you liked it and thanks for watching. Stay safe and stay healthy.